Hello everyone, my name is Bernard Sweers. I'm from CWI, the Dutch Research Institute for Mathematics and Computer Science. And today I'll present joint work with Guido Schaefer on maximum coverage with cluster constraints. I often work on logistics problems, and what you see there are that there are often two types of capacity constraints. For instance, you have a capacity constraint on the weight that you can assign to a container, and there's also a capacity on the ship itself. And that are the specifics of a cluster constraint that we will study. So we will assume that there are two levels of capacities, and we say that we have knapsacks, which are the first level of capacity, and they're partitioned into clusters. We need to find an assignment that satisfies knapsack and the cluster capacity constraint. Well, we will apply this idea to the general multiple knapsack problem first, and then to the maximum coverage problem with knapsack constraints. And for that we will develop LP-based approximation algorithms. Well, to start with the multiple knapsack problem, we'll just do a short recap. This is the ILP formulations. We have to decide which item to assign to which knapsack. That's the decision variable. Then the goal is to maximize the profit, make sure that the knapsack capacity is satisfied. Every item is assigned at most one. It should be integrally assigned. And a crucial part, especially for the LP relaxation, is that we do not allow an assignment of an item to a knapsack for which the item has a higher cost than the budget of the knapsack. In another way, wouldn't fit integrally. Well, this is just a standard problem, and the nice thing about it is that there's a constructive algorithm for the LP relaxation. The idea behind it is that you need to sort the items with respect to the efficiency, which is the profit of an item divided by the cost. And then you sort the knapsacks with respect to the capacities, the smallest knapsacks first, and then you add an item to the first feasible knapsack, and we will ideally assign it integrally, but you'll only assign an item fractionally if the knapsack has insufficient capacity. You just assign it to the next knapsack, that part. The nice thing about this LP relaxation is what we will call the bounded split property. And that basically says that there's every fractional assigned item can be matched to a unique knapsack. So there's only at most one item fractionally assigned to a knapsack. And with that, it's straightforward to derive a half approximation algorithm for the multiple knapsack problem. First step, you solve the LP relaxation. Second step, you match every fractional assigned item to a knapsack. And that's then the only assigned item to that knapsack. So integrally, that's a feasible solution. And then we have two integral solutions, namely the original integral solution and the one consisting of the fractional items. And if you select the most profitable of these two, you have a half approximation. Well, that's just a well-known algorithm, but the idea is crucial for understanding what we will develop now. So now we will assume a new problem, the multiple knapsack problem, with cluster constraints. We have a set of disjoint clusters, and we know which knapsacks are part of that cluster. Each cluster has a capacity, and we know that the cluster capacity, at the budget of a knapsack is at most the cluster capacity, because otherwise you can just reduce the capacity of the knapsack, and that all knapsacks in the cluster, their budget, the sum of their budget is higher than the cluster capacity, because otherwise it wouldn't make sense to have the cluster capacity. It's redundant. Well, you can just formulate with an extra constraint this ILP. It's the same as we've seen before. And the difference is now that we have a capacity constraint that's on the cluster capacity. and one it's on a knapsack level. So this is something that we cannot apply the technique we just seen, because we need to know how to divide the cluster capacities among the knapsacks. So we thought, well, it's a good idea maybe to introduce a decision variable, namely zkl, and it's just deciding which fraction of the cluster capacity is assigned to a knapsack. And if you use that decision variable, you can rewrite that cluster capacity constraint as follows, using these two constraints. And now the top constraint of the cluster capacity is on a knapsack level. The nice thing about that now is that we can bring it down to two knapsack constraints. The crucial part here is that we know that there is a critical knapsack, and the critical knapsack is just defined as the first knapsack. If you just take all the largest knapsack, the first knapsack that violates the cluster capacity. And then we know for these z variables that there exists an optimal solution to the LP relaxation, for which you just open the largest knapsacks first. You open them completely. So you just allow the original budget to be assigned to that. For the critical knapsack, you just open it as much as possible, and all smaller knapsacks, you do not open them. You don't induce them at all. Well, and knowing these optimal solutions, we can just say that there's a reduced capacity for a knapsack, which is just the minimum of its original capacity and this capacity it gets from the cluster. And that's just for all knapsack larger than the critical knapsack, its original budget, and otherwise it's an adjusted budget, which is UL times Z star KL. So now we basically have a multiple knapsack problem only with new capacity constraints. So it's really natural now to think, well, we have a half approximation. But unfortunately, that's not the case. And to see that, we use F to denote the fractional assigned item to a knapsack. And it could be that the fractional assigned item to the critical knapsack it's definitely not more than a budget of the critical knapsack, but it could be more than the reduced capacity of the knapsack. And if all other knapsacks have an assigned item whose cost is exactly the budget, then the fractional part violates the cluster capacity. So unfortunately here it's not a half approximation, but we can derive a third approximation. Namely, you just take the maximum profit from the integral assignments, which is always feasible. You just take the budget of the fractional assignment of the critical knapsack on itself, which also always is a feasible solution because it does not violate the cluster capacity. And then the same holds for all other fractional items, because we assume that the critical knapsack is the first knapsack for which the budget violates the cluster capacity, the budget of the knapsack. So that means that because the fractional assigned items always less than the respective than the capacity of the respective knapsack, these items should also be at least, at most, the capacity of the knapsack. Now we can generalize this multiple knapsack problem to the maximum coverage problem with knapsack. And with that, we need a set. And the set has now a cost, and every set contains a certain items, and these items have a profit. The goal of the problem is to find an assignment of sets to knapsack such that the cost of the sets covered by a knapsack do not exceed the budget of that knapsack, and that the profit of the covered items is maximized. Well, the RP formulation is given here, and it's basically the same as we've seen before, but now we have the yi variable, which indicates whether an item is covered, and the xjk variable says whether a set is assigned to knapsack k. We use x star LP and y star LP to denote an optimal solution for the LP relaxation. But if you know the optimal solution for which sets are assigned to knapsacks, it automatically follows which items are covered. So we will also only refer to x star LP to the optimal solution of this LP relaxation. This is without cluster constraints. Only the maximum coverage problem with knapsack constraints. Well, there is no existing LP-based approximation algorithm for this problem. And the downside of this formulation is that the optimal LP relaxation does not satisfy the bounded split property. So what we will do is we will look at the pipage rounding formulation. And that's given here. As you can see, the constraints are the same. So every solution that's feasible for the linear relaxation is also feasible for the pipage rounding formulation. And the objective function is different, but if the this part here is integral, then the solution for this pipage rounding formulation is the same as for the linear relaxation. The nice thing about this pipage formulation is that it's quite that it's shown before that the feasible solution of the LP relaxation is the pipage rounding formulation is at least 1 minus 1 over e times the solution of the LP relaxation. So we will show now that you can change the optimal LP relaxation solution into a solution that satisfies the bounded split property, and for which you do not increase the objective function, do not decrease the objective function of the pipage rounding formulation, which means that we have fx is at least 1 minus 1 over e times the linear solution of the LP relaxation. To do that, there is a crucial concept, and that's the support graph of a solution, a fractional solution. And that's given here. It's a bipartite graph. On the left-hand side, you see all the sets. On the right-hand side, you see all the knapsacks. There's only an edge between a set and a knapsack if that if the corresponding variable is truly fractional. So if it's between strictly between 0 and 1. Well, then we show first that there is an optimal solution to the LP relaxation whose support graph is acyclic. Consider this example. Here we have a cycle. But what we can do is that we just shift the same amount of contribution from, for instance, according to these arrows. That means that the total amount of x for set 2, for instance, that is covered is not changed because it just assigned more to knapsack 1 and less to knapsack 2. And if we just move around these things, there will be at one point one edge that will be either 0 or 1, which means that we can remove that edge from this graph. And we haven't changed the objective function for this solution. So that basically means we can, for instance, remove this edge, and we've removed a cycle, and we haven't changed the solution of the LP relaxation, which proves this lemma. I will not go into all the details of the proof, just give the idea. Well, now we have this graph, no cycles anymore. Then there's the next lemma, and it says there exists a feasible solution of the LP relaxation whose support graph is acyclic and doesn't contain any SS paths, and whose solution for the Pipert-Rounding formulation is at least the Pipert-Rounding formulation of the LP relaxation. Well, what is an SS path? That's a path going from a node in S to another node in S. Now we'll show that we can remove an SS path without decreasing the Pipert-Rounding formulation. Well, to see that we can basically have two extremes. We either can push the contribution we have from node S1 all the way according to the path you see in the left hand side to node S2, or you can do it the other way around. And at one point, again, there will be an edge that's either 0 or 1, and then you stop. But these are the most two extreme parts you can get. And we can show that the function fx epsilon is convex in the interval between these two extremes. And since the function is convex, you know that the maximum of that function will be in those two extremes. Which means that if we take the maximum of these two solutions, we can show that we haven't the objective function of the Pipert-Rounding formulation has not decreased. So that means that we can remove, for instance, this edge from the graph. Well, then we've got another SS path, and basically we can do the same. So, for instance, remove that edge. Now we're left with this graph. We don't have any cycles. We do not have any SS paths anymore. We only have paths that starts in node S and ends in a knapsack. Then we know that if a graph doesn't have any cycles, doesn't contain any SS path, then it should satisfy the bounded split property. For instance, here you can just see that easily there is a matching between all fractionally assigned sets and the knapsacks. So, concluding, we have an X star LP, which is the optimal solution for the LP relaxation. And we can change that into a solution that satisfies the bounded split property and whose X solution is at least 1 minus 1 over E times the optimal LP relaxation. And if you just select the most profitable of these two solutions again, you get a half times 1 minus 1 over E approximation algorithm. Now we'll go to the maximum coverage problem with cluster constraints. So now, basically, before we only had knapsack constraints, but now we can basically combine the idea we had for the multiple knapsack problem with cluster constraints with this maximum coverage problem with knapsack constraints. So you use that Z variables to construct an instance of the maximum coverage problem with knapsack constraints, and then you use Pipert rounding to obtain an X that satisfies the bounded split property, and then it just basically follows now that you lose, again, you go from a half to a third. So you have a third times 1 minus 1 over E approximation algorithm. So the conclusion is that you can using these Z variables, it's possible to extend capacitated problems with a cluster capacity. You can use existing or new LP-based approximation algorithms to solve these problems with cluster constraints. What's also new here is that we use the pipette rounding to partially round a solution of the maximum coverage problem. And in future work, now we've just studied 2 problems with one level of capacity, but it's quite natural to extend these ideas to other problems with capacity constraints. For instance, we have some preliminary result that it also applies to the capacitated facility location problem. It's also interesting to see, and that's maybe a bit more tricky with this formulation, if it can be applied to problems with the cardinality constraint. And maybe less practical application, but theoretically maybe interesting, is to see if you can also apply this technique to problems with multiple levels of clusters and not just a single level. So then you have a cluster of clusters. And it's would also be nice to see if we can improve on the approximation ratios we've shown you. In the paper, we showed that for a specific instance of the multiple knapsack problem with cluster constraints, we get not a third approximation, but a half approximation. It would be nice to see if we can do that for more general problems. Thank you for your attention.